Hey everyone, welcome back to Rocks for Jocks. My name is Alex, and I'll be your host for the show. Today I'm hosting Andy Jones, who is a PhD candidate at the University of Wisconsin Madison. He studies glaciers and climate science, and he's going to tell you all about that today. So it should be a good one. If you like this episode, please send it to a friend or family member, and subscribe wherever you're listening. After that, go subscribe to Rocks for Jocks on Substack. Every time I post a podcast or an article, you'll have that sent straight to your inbox every month. Thanks for listening, and yeah, enjoy the show. Thanks again for meeting with me. I guess what would be great to start is if you can give me maybe like a brief 30-second introduction about a little bit about who you are, kind of your current role, and what you're researching.
Yeah, so I'm Andy Jones. I'm a final year PhD student, technically PhD candidate at the University of Wisconsin Madison. I study glaciers and climate science in the Department of Geoscience here. Yeah, I mean, I think glaciers are really interesting, sort of like look-ins to the past. They tell us about temperature today and also in the past, so we can reconstruct what they did and get a sense of what climate was like a long time ago.
Perfect. Okay.
That's why I like it. Yeah.
Yeah, I'd love to hear more about that. Could you maybe tell us a little bit about glaciers in general? Like what exactly are they? How do they work?
Okay, so when people think about glaciers, I mean, I think maybe you might think of Antarctica or Greenland, right? These are massive ice sheets. They're like the glacial equivalent of a, pancake batter on a pan. They're just big and they're flat and they're wide. What I study is mountain glaciers. So you can picture like Switzerland, right? It's the Alps, right? Classic. There's sort of like ice flowing down a mountain, maybe, yeah. And what a glacier is fundamentally is year to year when you have more snow than you lose to melt and the snow builds up, right? Year after year, right? You get ice that forms and it's on a slope, so it flows downhill. And it's these sort of like basically giant ice cubes just like slowly rolling their way down the hill, slipping and sliding, doing a little bit of erosion of the bedrock. And yeah.
Cool. Yeah, that was something I was thinking about when I was getting ready for this episode, is that the only glaciers I feel like I ever heard about growing up were giant ones in Antarctica, and then I stopped hearing about them after maybe early middle school until I got to
Yeah.
late into college, and started working with a couple of professors who were looking at them in their own research and hearing about them secondhand, third hand. We don't encounter them in our daily lives at all. So I guess, can you maybe tell us a little bit about also like why glaciers matter, why they're important, and kind of what they do for
Yeah.
the Earth?
Yeah. So I mean, again, talking about mountain glaciers. So the research I've done was in California, Sierra Nevada, in Yosemite National Park. If anyone's ever walked on the Pacific Crest Trail, or the John Muir Trail in Tuolumne Meadows, right, you can look up and there's sort of like snow and ice up there, on sort of the caps of the mountains. It's very pretty, iconic, you might say. And these glaciers, they provide stable meltwater to the streams when all the snowpack is melted for the year. So their ecological role is one of stability. That's probably the most important function in a place like California. And there are other places like in the Himalayas or in the Andes where glacial meltwater is a huge source of drinking water for communities there. Again, right, you get a bunch of snow in the winter. You can think of it's like a water tower for a lot of these communities, and that snow melts and it goes into rivers, right, and people end up drinking it. When that snow is melted for the year, there's parts of the year where you just have ice melt that keeps everything stable and flowing. And when you lose those, it's a different environment, certainly.
Okay, great, thank you. And digging back a little bit here to my own days in college, if I remember right, there's also some aspect of gigantic glaciers down in Antarctica, reflecting sunlight and keeping the Earth like a little bit cooler
Hmm.
as time goes on. Is that right?
Yeah, yeah. So that's the albedo effect. The idea being, I mean, you can feel this when you live in a city, right? It's a hot blacktop, it gets really toasty, or yeah, or white car, dark car. That's always a good analogy too. Yeah, the ice sheets themselves have a cooling effect, where the sunlight hits it, it bounces off, it's shiny and white, or it doesn't stick. And as they get smaller, you're replacing sort of that area that was formerly like bright and white and shiny with usually dark, like brown or gray land, or rocks, they warm up proportionally more. So it kind of has it's a positive feedback, we call it, right? It's sort of um, once the dominoes start going, you can get tough to reverse.
Got it. Right. So the more the ice sheets and glaciers shrink, the less reflection takes place, so things continue getting a little bit warmer.
That's right.
Can you tell us a little bit about the process of like how glaciers expand and retreat? Like what that means exactly when we say
Yeah.
a
hmm
glacier shrinks?
hmm Yeah. So I wanted to say this earlier. So you can think of glaciers as having a budget. If you spend more money in a year than you earn, you're going to lose money, right? If you make more money in a year than you spend, you're making money. That's great. Glaciers are the same way. So it's about the amount of snow you get compared to the amount of melt you have at the terminus, right? And usually it's high up. This is where the snow comes in, right? And then the glacier flows downhill. It melts at the bottom. So glaciers never literally retreat. Right? They don't go backwards. They're always flowing downhill. The analogy I like to think of is a grocery store conveyor belt or something, where I imagine you can grow the conveyor belt, right? And it's gonna always everything's gonna work to one side, and you're carrying rocks and debris, right? You have your imagine a soup can making its way down, and everything collects by the register. But then you can shorten that, right? So when the glacier retreats, it's just becoming smaller. Really, the technical term is recedes or glacier recession is really what it is, right? You're just sort of shrinking the conveyor belt, but everything's still flowing downhill. And again, when it's colder, get more snow, glacier's going to be bigger. When it's warmer, you're having more melt. The glacier will ultimately be smaller, and at a certain point, they will go away entirely if you're no longer getting any sort of snow preserved year to year.
Okay, great. So maybe that's a good segue then to talk about the glacier that you were focusing in on in California. Yeah, can you tell me a little bit more about that one?
Yeah, so our study came out showing that glaciers in California, Sierra Nevada are disappearing for the first time in the past 30,000 years. We went to glaciers in Yosemite National Park, the Lyell and McClure glaciers. And these are sort of interesting glaciers because they're some of the first in Western North America to have documented ice flow. It was John Muir who went with like wooden stakes up to the ice in the late 1800s, put it in, and came back the next year and saw they had moved. And he said, "Oh my gosh, the ice is flowing. Right, that's the only way." Um, they have a long history of being studied. There's mapping from the late 1800s. There's historical photographs showing how much smaller the ice is today. But nobody knew in a deeper time context what the ice had been like. And that's what our study did. Is we came along and we said, it turns out these ice bodies that people had thought were ephemeral, sort of coming and going, in sort of the last 10,000 years, in which sort of comprises most of right agricultural history and human history, recorded human history, that is. And it turns out they've actually been around for that whole interval, and actually even prior to that, because the last glacial maximum, when glaciers covered all of Canada and parts of the U.S., that was 20,000 years ago. So you can just extrapolate backwards, like, oh gosh, there's been ice there probably for longer than there's been people in the Americas. Meaning that when it goes away, it's going to be a very different circumstance.
So it sounds like the glaciers that you're looking at have been in North America since before humans have been here. Can you talk a little bit about maybe like the history that we have of them so far and kind of what researchers like yourself have been able to put together about their history in the last few decades?
Yeah, yeah. So what we know is that there were giant ice sheets over Canada and the northern part of the U.S. If you're based in Boston or anywhere in the Midwest, there's these old deposits. Long Island's a glacial moraine, right? We know there's just massive amounts of ice over the northern part of the U.S. 20,000 years ago. Um, and people think it was probably really from 30,000 until maybe 12,000 years ago. Yeah, there's just massive ice sheets here. And the same is true for California and Sierra Nevada, where there was an ice cap covering the mountain range through this sort of glacial period. And at some time in that window, it's thought that the peopling of the Americas happened, um, either through the corridor between the ice sheets or along the coast, sort of this sort of new sea ice highway idea. But I digress. Right, and there's been footprints found of people in the U.S. 20 some thousand years ago now in the White Sands footprints, which is really remarkable. Um, anyway, and then we reach sort of about 10,000 years ago, and this is sort of this happy climate interval known as the Holocene. This is sort of when things stabilize. So the last 10,000 years have been actually really consistent, and it's no accident that agriculture flourished during this time because you could really reasonably predict climate from one year to the next. And yeah, within this window, still people had thought in California glaciers had sort of come and gone. And this was based on lake sediment records where you can sort of like glaciers they're eroding the mountain and they make this sort of fine silt. It's called rock flour, actually. If you've ever gone backpacking to try and filter your water near a glacier, it clogs your water filter. Super annoying. Um, yeah, and you can actually measure that in the bottom of a lake. You take a core and you can go down and say, oh, look, there's rock flour. There must have been a glacier here. And if you don't see rock flour, you say, oh, there wasn't a glacier here. And that's what people had done before. And this method is good. There's nothing wrong with it. However, sometimes we think there's limits to what you can detect for rock flour. So maybe if you have a really small glacier, it's hard to discern, right? Like, was the glacier there just not doing much, or was it not there? And I think that's where our research came in. And we sort of more directly, I would argue, dated whether or not there was ice sort of in the highest reaches of the mountains.
Yeah, so then tell me a little bit more about that and your team's approach to researching where the glaciers
Mhm.
were.
Yeah, so we walked ourselves up to the fronts of the modern glaciers, and this is not a trivial hike, right? You got to get up to I think at Donahue Pass in yeah on the PCT if anyone knows that. You're getting up there. It's one of the higher points that you'll do. And we actually, yeah, we walk up to the front of the ice. You can literally put one hand on the glacier and you have your foot standing on bedrock. And the idea is that we can date when the last time the bedrock was exposed to the surface of the earth, not covered by a glacier. The analogy I think of is charging a battery with a solar panel. When there's no glacier covering your bedrock, right? It's receiving um, energy from space and it charges the battery. And then if the glacier were to rebury it, you would cut that off, and then you actually would now have a bit of radioactive decay. So your battery loses charge, if you will. Right? Because we're talking about it's like technically radioisotopes that are accumulating in the rock, but details. Um, what we found was no charge. When we took the samples back to our lab, right, we literally chip off like, uh, hand-sized pieces of rock, fill our backpack with rocks, walk out 12 miles. It's not that fun. Um, and we found, yeah, they hadn't seen the surface of the earth in a very long time. Um, and then we use sort of geologic evidence to say, wow, the last time these even have a chance of seeing the surface of the earth, if not for the past 10,000 years, was over 30,000 years because we know where ice was during the glacial period.
So to recap that, it sounds like you're measuring two things. You're measuring, first of all, how long the rock was exposed to light, and then secondly, how long it's been not exposed, like how long that
Yeah.
radioactive decay has been going on. Is that right? Am I on the right track here?
No, you're totally right. We technically we're measuring two nuclides, two isotopes. One of them is long lived, one of them is short. It's actually radiocarbon produced in rocks, which has a pretty quick half life, like 5,000 years or so. The other one it's like over 1 million years. So we can actually detect not only intervals of exposure, but also burial because they decay at different rates. So you can do the math. Say, oh, look, we have more of the long-lived nuclide and less of the short one. That's right. It's because this one decays much faster. You actually can say, okay, that means this rock was buried for 3,000 years and exposed for 8,000 years. But again, what was unique about this study, in comparison to other places we've gone, was that there was no charge at all, which tells us, wow, this hasn't seen the light of day in a really long time. Um, Whereas other places we've gone in the Western United States, even, um, you could say, oh, glaciers were actually a little bit smaller than they are today, like 8,000 years ago.
Wow. So you were able to figure out that that glacier's been covering the currently exposed rock right at the edge of the glacier. That rock has
That's
been
right.
covered since well before humans have been around. What do you take away from that then?
Right. Yeah. So, I mean, you think about in science class, right? You have your hypothesis, methods, results, discussion. That was the result. Our methods, shipping the rock, we're measuring the isotopes. Our big result is like, huh, these things are blanked. There's nothing in them. There's no charge. So in our discussion section, we're like, okay, what does this mean? There is a few ways to explain it, and this is what sort of the paper gets into. The first one, the simplest one, I think the best idea, is that there's just been ice over that bedrock for, again, the last 30,000 years until now, right? Until human caused warming, industrial era warming, caused glaciers to melt back enough to expose this rock, it's been covered by ice. So it sort of demarcates where we are today relative to our past, right? I mean, literally, no other person would have set eyes on a glacier-free peak in the Sierra Nevada until this century when these glaciers go away. That's sort of the bottom line interpretation. The other hypotheses, it's technically possible, right? I wasn't there. What if there was a landslide? The glaciers are gone 8,000 years ago, but there's a landslide from right, the cirque, sort of the walls of the mountain, sort of just sloughing off and covering the bedrock. And then the glacier reforms, pushes that bedrock down the mountain, and right, the bedrock never sees the light of day, but we don't know the difference. That was sort of the main competing idea we had to deal with. And we go through all the different lines of evidence, and we say this is pretty unlikely because we sampled sort of these sort of bedrock knobs, sort of like relatively high points that were out in front of the ice, and they still show burial. Right? Imagine there's a landslide, right? You would think that the knobs might poke out and protrude still. Is it? Could you have had just a giant boulder over every single one of the sites we sampled? We went to 12 different samples, 12 different little bedrock points. I mean, you could have. Seems unlikely. And then lastly, there's this thing called the glacier moraine, which are these deposits that the glacier makes. Right, they're big sort of piles of debris. Again, think of our conveyor belt analogy, where you're moving all of your grocery cart items down to the register and just building up. That's the rocks are building up in a big rock pile. It's called a moraine. We dated the rocks on there as well, and they were consistent with the ice sort of being at a larger position, sort of near its largest position of the past 10,000 years for maybe the past 3,000 years or so. And had there been a big landslide that sort of covered all the bedrock and then moved all those boulders down slope and put them on there, you would think you'd see some evidence for that in the moraine dates that we have.
Okay. It sounds like that leads you guys pretty squarely to the conclusion that it's almost certainly been covered by glaciers for
In
a very long period of time.
in scientific parlance, we would say that it's likely glaciers persisted through the past 30,000 years.
Fair.
Because right, and everything is a hypothesis until it's a theory. Everything can be proven wrong. We are committed. I mean, it's so funny. I think climate scientists are ruthless against each other about their ideas. And we are the most skeptical. We come after each other all the time, saying like, "Hey, you haven't supported this enough. Like, what if it could be this?" And I think it's very funny that our community is often, sort of accused of groupthink or something. I mean, we like rip each other apart. So only the best ideas stay. And again, we're committed to say, hey, if someone comes along with a better idea and proves me wrong, awesome. That's good. That's progress. That's science.
Is there any studies that you've seen, any methods, I guess, that others have done around you that you've thought to question and kind of push back on them a little bit on?
Yes, there are. So in this paper, people had thought glaciers were gone and then reformed, and that's honestly what we were going to test. We figured that's what we would get based off these sort of lake coring methods that I had talked about. And again, I don't think lake coring methods are wrong. Right, the prior work isn't wrong. You core a lake and there's sediment, and you can see different changes through time. That's totally real and valid. The question that we had is, how hard is it to tell a small glacier from a completely missing glacier? And that was, I think, where we pushed back a little bit on the community to say, like, maybe it's more difficult to make that distinction than previously thought. And really, you have to, again, in science, you have to bring all the evidence to the table. And our argument is like, well, those lake records now have to account for our bedrock exposure dates that are right, basically zero. So you have to make it all work. And again, I think a way that makes it work is that you have sort of small, slow flowing glaciers, potentially with sort of this debris cover, like actual rocks on top of it that are shielding the glacier from some of this melt. They sort of have it's sort of like a blanket over the glacier, debris layers. Kind of nice. And allows them to hang out in conditions that otherwise are unfavorable to glaciers. And there's other places in the Western US where people have seen sort of those debris covered glaciers transition to sort of full, more erosive glaciers. And we said it's totally possible the same thing could have happened in California, and that would actually make sense with the lake records and why you don't see sort of a strong rock power signal earlier on.
As far as the, I guess, climate and environment in the Western US, do you have a sense of what either temperature or humidity or any other factors in the environment affect glacier growth and retreat? And to what extent is there like an optimal temperature that they like to stay stable at versus when it hits thresholds for starting to recede and grow again?
Yeah. Um, so people think about this. There's like you can almost imagine it's like a line in the sand that you can draw on a glacier, and above that line you'll have snow all year long. Like the snow never melts, and then below that actually the snow will melt out. And that's sort of the accumulation area where the snow builds up, and then sort of the ablation or melting area where it melts out at the base. Um, as temperature warms, that line goes up, right? You have less and less of the glacier's area that's going to be persistent snow all year long, even through the summer. And at a certain point, the line will get so high that the entire glacier will actually be in the melting area during the peak of the summer. But you've melted through the snow all over the glacier. And once that happens, you can sort of cross a non-linear threshold. You're just like, oh gosh, the whole thing is melting now. So this thing is going to go away, right? Because you just can't sustain it if there's no snow being saved year to year, right? You're basically running a deficit, if you will.
Okay, that makes sense. And then do you have ballpark temperatures of what temperatures the glaciers in California like to sit at?
Yeah. So I don't, we don't really think in absolute temperature so much for glacier change or sort of long term climate change, just because it's a little bit difficult. It's easier to say like 2 degrees warmer than modern. I
Mm.
think that's something we can more reliably measure. It's hard to, I mean, there's people have thermometers up by the ice and measured that, but um, obviously it has to be below freezing to have snow year to year, right? It has to stay like at least the surface of the ice has to stay below freezing the whole year in the accumulation area. Um, Whereas, yeah, the melting part, right? I mean, the ice is melting, so the surface of it is just warm enough to melt, probably 32 degrees Fahrenheit. Um, but yeah, in absolute temperatures, I mean, this is what's interesting. So we think, okay, so for the last 10,000 years in Western North America, we think climate was actually a little, either maybe about as warm as today. People might argue it's sort of a summer thing. So summers were about as warm as today. And glaciers are very sensitive to summer because, like I said, that's when the melting is happening. Um, And then, this is about 8,000 years ago, right? And then slowly over many thousands of years, gets colder and colder and colder, and it eventually culminates in the Little Ice Age. This is a interval of time you may have heard of if you've seen like pictures of medieval Europe when everyone's just freezing cold. Like there's some volcanic eruptions too where the sun went away for a whole growing season and caused a lot of famine. People died. Um, but anyway, it got really, really cold in the Middle Ages again because of this long-term progression of just it has to do with changes in the Earth's orbit around the sun. But anyway, and then in the last 100 years, we've gone from basically the coldest period of the last 10,000 years to the warmest. So what took thousands of years to grow, right? These glaciers, almost overnight, in geologic terms, they've melted to their near smallest positions of the past 10,000 years. Funnily enough, so you hear the number 2 degrees Celsius thrown around a lot. If you're working with or thinking about climate change, that's about what we think is that 8,000 years ago it was probably about summers are about 2 degrees Celsius uh, warmer than like pre-industrial temperatures, um, and it actually makes sense that the planet's approaching about 2 degrees Celsius of global warming from pre-industrial temperatures now, and we're seeing right? We're sort of crossing that line in the sand for glaciers sort of becoming unprecedentedly small relative to their sizes over the last 10,000 years. Right? It sort of makes sense. It was 2 degrees warmer, right? We've cooled. Now we've gone up 2 degrees, and the glaciers are right back where they were many thousands of years ago. Although we did it in 100 years.
Do you find that there's any kind of a lag between when the warming starts to happen and when glaciers start to recede, or the opposite? If times get a lot colder and snow starts falling a lot harder, and the surface of the glaciers gets colder, how long it takes for them to start growing again?
Yes. Yeah, totally. I mean, so it's related to the size of the ice. So something like Antarctica, massive ice sheet, like bigger than the continental US. I mean, it's huge. It can take almost 1,000 years for a glacier like that to fully adjust to a warmed climate. And this is why sea level rise is so tricky to project because it takes a long time to catch up. So we've warmed the planet really fast in 100 years, but the glacier's still behind the eight ball, so to speak. It's just playing catch up. And people have spent a lot of time trying to project what the glacier will do over the next 50 years or 100 years, these sort of shorter or 20 years, timescales that are more relevant to us. But we can tell you, yeah, in 1,000 years, it's going to melt this much. That's easy. The question is what's going to happen in 20 years. But anyway, mountain glaciers, much more sensitive. They're smaller. Again, I think of like a high inertia system versus a low inertia system. You can imagine, right? The Titanic, it sees the iceberg coming, it tries to turn, it's too late, right? It's a giant ship, lots of inertia. That's sort of like Antarctica. A mountain glacier would be like a little tugboat. It sees the iceberg, it says, okay, and I'm gonna turn and I'm gonna deal with it, right? It can respond quickly. So a mountain glacier, within 20 years or so, will like after warming, will start to show the signs of that warming, perhaps even quicker. So they actually are responding in real time. There is a lag. I think the glaciers are still catching up. Like if you were to pause warming right now, they would still retreat a little bit because they're a little bit behind. But it's 10, 20, 30 years, not like 500 years like Antarctica or Greenland.
Is there any kind of a lag as well between how long it takes for if we were to try to cut down on greenhouse gas emissions, for example? How long would it take for the general global temperatures to adjust? If we cut off all greenhouse gas emissions tomorrow, does the temperature stop rising immediately, or does that kind of continue onward
It
for
keeps going.
another couple of
Yeah.
years or something?
If you were to hold greenhouse gas emissions totally constant, like from right now, you would still see global warming. You would still see sea level rise. Um, and this is why I think a lot of people are pushing towards getting that carbon back in the ground. Yeah. So if you cut emissions down to zero, there's still elevated levels of carbon dioxide in the atmosphere. I think we're at like 420 parts per million right now. Um, people have said 350 parts per million would be a reasonable target. If you go back a little before that, we're probably talking about 300 parts per million, like before the industrial era. Um, so we're already way above levels that our forebears would have seen here on Earth. And again, especially the ice sheets have a really big lag. It can take them hundreds of years to catch up, which is again, I think so. It's why people say, okay, not only do we have to stop emissions, but also actually bury that carbon back underground, is so that you can stave off some of the worst impacts.
So to recap for the listeners, I want to make sure I kind of capturing the essence of what you're saying here. The thought process behind being like really conservative when it comes to releasing greenhouse gases rather than rolling the dice with it is that it takes time. Even if we cut off all greenhouse gas emissions now, it would take time for the earth to stop warming. And then even if it stops warming, it would take even more decades for glaciers to stop melting and other effects to keep going on.
Yeah, definitely.
That's the way I think about it, at least. I want to see if you think about it the same way or if anything
Yeah,
else you want to tack onto it.
no, I think that's totally right. And again, there's sort of two races going on. One is to just stop the bleeding, right? We got to get the emissions to, they're going up every year, right? It's like people say, oh, emissions went down last year. It's like, no, the rate of growth of emissions went down. Like the absolute amount of emissions is still going up. Right. And imagine to have net zero carbon, the first thing you have to do is have actually zero emissions, right? Or you're sequestering, like burying carbon that's in the atmosphere. Unless you have some emissions, but you put away more than you make. That's one race. And then secondly, in the scientific community, people are racing to understand what different amounts of CO2 are going to do to the planet. If you just say, okay, if let's say we're going to settle at 350 or 400 or 450 parts per million carbon dioxide in the atmosphere, what does the Antarctic ice sheet look like? And what we do is we turn to the past. And we say, okay, when was the last time CO2 was about 420 parts per million, like it is today? And it turns out in some of those intervals, yeah, the ice sheets were a lot smaller and sea level was a lot higher. And that's troubling because, again, back then, right, they didn't have Miami or New Orleans or Jakarta, these major urban populations along coastlines with history and culture and humans living there. Um, yeah, climate change is a human problem. If there's dolphins at the North Pole, that's fine, but we don't want to have to move our way of life in our cities.
Yeah. No, that makes sense to me. Can you tell me a little bit about what else you're working on, your other research projects that either tie into this one or if they're pretty different topics? I'd love to hear about those as well.
One of the other papers that I worked on in my PhD was a similar finding from the tropical Andes. So showing that glaciers in the tropical Andes, so this is in Peru, Bolivia, Colombia, are also sort of crossing that line in the sand. They're reaching their smallest size the past 10,000 years right now. We did the same techniques. We found similar results. Um, for the rest of my PhD, I've been working on not only walking up to the ice and collecting bedrock samples right where the glacier is exposing them today, but actually sort of collecting samples down valley from the ice, sort of towards that deposit I talked about, the moraine, to get a long-term sense for glacier growth and then ultimately glacier death, right, in the present when it's retreating. I think if we were to understand what we're doing to glaciers today, we not only need to know the last 100 years, but we have to actually reconstruct in space their size changes for many thousands of years um, to give necessary context for their loss.
And how's that project going so far? What stage of that are you in right now?
We've completed it at a few sites. Um, like in Alaska, we have research coming out showing that the glacier has receded to a size it hasn't occupied for about 5,000 years. Like 5,000 years ago, it was last this small. And then over, like from 5,000 years ago, sort of marching forward in time, um, right, it was like, it only really reaches its pre-industrial size relatively late, actually. It's like, sort of, it progressively grows over hundreds, thousands of years. And then a couple hundred years ago, it reaches its maximum. And then boom, all in 100 years of loss, we've uh, retreated back to that size we haven't seen for 5,000 years. So in that case, again, I think the rate of change is what jumps out to us. It took glaciers a long time, thousands of years, to grow to these extents that they were at before the industrial era when greenhouse gas emissions really took off. Um, and we're losing that again almost overnight in geologic parts.
It's a tough field to be in and try to keep that optimism on a day-to-day basis would be my guess. What do you kind of look towards to kind of keep that North Pole in your
Yeah.
head?
The thing that motivates me is that every action that we take matters. Everything, like every gigaton of carbon that we keep in the ground is less carbon that's going to cause warming. And it's very clear from the research that our decisions matter, right? If we warm up by 4 degrees instead of 2 degrees, it's a radically different scenario for global sea level rise, which is really the one of the biggest problems of climate change, right? Because that's our infrastructure having to be moved, which is not impossible. Yeah, our decisions matter, and that's what motivates me. Is that continuing to study these questions, to learn more about the past, it tells us more precisely what we need to do going forward.
Fantastic. Last question I'm going to ask here. Do you have a favorite project that you've worked on during your time in graduate school? And I'll even include college in there, either research or just for a class, or maybe you were like a, I don't know, seventh author on somebody else's paper that you just thought was really interesting and want to talk about.
Honestly, this was my favorite one. Like this project, this about California was, I've been working on this for 5 years. We had a lot of internal discussions, again, trying to get the interpretation right. Um, and this was, I don't know, this was my baby. I was really invested in trying to get this one over the finish line. We went back, yeah, twice after sort of the initial field campaign. Um, that was pretty exciting. I mean, also the paper from the tropical Andes too. I was just on the author list for that paper. That one meant a lot as well. Especially I think because communities in South America really depend. I mean, the glaciers are bigger. They supply a lot of meltwater to people. I had the pleasure to go back and collect some more samples from Bolivia this past summer. Um, yeah, and we had good conversations with our hosts, sort of indigenous stakeholders in the community about what mean for them and their water. I mean, there's a big reservoir out in front of the house where they live that collects the glacial meltwater that ultimately serves as sort of the water tower for La Paz, Bolivia, the city there with million people living in it. It's real, right? When you go into the community and you have a conversation, and I think that was really powerful.
Sure. Is there anything else you want to share with anybody else listening?
I mean, I've hit most of my talking points, but yeah, I think what we found was that when glaciers in California, Sierra Nevada disappear, it's going to be for the first time in the past 30,000 years, meaning we will be the first people to lay eyes on ice-free peaks in California, Sierra Nevada. Um, and I think that's tangible, right? It's like you can people talk a lot about 2 degrees Celsius of global warming, and I think to many people that feels sort of imperceivable, right? You're in your house, well, 2 degrees. I mean, that's meaningless, right? You couldn't possibly tell the difference. But glaciers, they're physical, right? They're touchstones between the past and the present. When these glaciers die off, right, we're going to be the first humans to see ice-free peaks in Yosemite. I mean, the national parks are places that we, as a society, right, as a government, we protect this land, and so much goes into the conservation of this land. And yet, global warming is everywhere, right? It's omnipotent. It's like insidious. No matter what we're doing to conserve the glaciers, are still going to melt because everybody on the planet is feeling global warming, including the ice.
Thank you so much, Andy. I'm going to pause the recording here. If you've made it to the end of this episode, I'm here to let you know that you are legally required to subscribe to Rocks for Jocks Substack. Click the link in the description to this episode to enter your email and receive a free podcast and newsletter delivered to your inbox every month. Thanks for listening.